This video is a review of graphing polynomial functions. In reality, it might be the case that only a little bit of this is actually a review and a lot of it is new for you, but I hope that in either case, it's still useful for you to see this. So for starters, we need to ask the question, what is a polynomial function? And all three of these things on the top are examples of polynomial functions. So what makes something a polynomial function? Let's focus on a couple of things. First, you want to look at the powers of x. So we see, for instance, in this top example, we have an x squared. We have 5 times x squared. We also have an x to the first power. There are 0 x's to the first power, and we have negative 3 copies of x to the 0. So we could actually write this as 5x squared plus 0x to the first plus negative 3 times x to the 0. And basically the point that I'm trying to make is that what we see is there are whole number or integer powers of x, but non-negative powers. And then furthermore, the coefficients of those powers of x have to be real numbers like 5 or 0 or negative 3 or 0.36 or negative 2 and so on. One thing you definitely don't see are any powers of x like x to the 1/2 power or x to the 4.5 power. And in fact, the point is that this example down by the bottom is not a polynomial. The only way a function is a polynomial is if those powers that are involved are not negative and they are whole numbers. So because of this 4.5 power, that is not a polynomial function. And the same thing here. This function has an x to the -3 power. And by the way, x to the -3 stands for 1 over x to the 3rd power. And again, because our power of x is not a non-negative whole number, a non-negative integer, that forces this thing not to be a polynomial function. One really important thing in dealing with polynomials is that there might be several different ways to write a polynomial. For example, in this top one, f of x is written in a way that shows us what the powers of x are and what the coefficients are. And that's certainly kind of the way it needs to be written to make sure that it is a polynomial. But you have the option to write it in different ways. And this way underneath it is what we tend to call factored form. It's a lot like taking a number like 24 and writing it as 2 times 2 times 2 times 3. That's the factored form. That's the prime factorization of the number 24. And so what we have here is a factorization of the polynomial f of x. Same thing is true in the second example. This standard form shows us the powers of x that are involved. It shows us all the coefficients. But this factored form is actually going to be really helpful for us when we go to graph that polynomial. And the same thing down here. This standard form shows us that we have 2x to the 3rd power and so on, but this factored form is going to be really useful when we graph h of x. Our first example is going to be a pretty easy one. This is what we call a degree 2 polynomial or a quadratic polynomial, and we call it a degree 2 polynomial because the highest power of x is 2. And it's written in both the standard form as well as the factored form. Now, if we want to graph this thing, the most naive approach we can take is to maybe make a chart of different values of x, and then what are the corresponding values of y when we plug those x values into our function. And so we could make a list like -2, -1, 0, 1, 2. We don't have to do whole numbers. We could do 2.5, 3, and so on, and plug all these things in. And that's certainly not incorrect to do that, but it actually is a lot of work. I mean, just to compute something like f of 3, well, let's do f of 2 instead. F of 2, if we use the standard form, we would get 2 squared minus 2 times 2 minus 3, and we have to go and do this computation, and we see that we get -3. And that actually shows us why this point, 2, -3, is on the graph of this polynomial. But in reality and in practice, it's just time consuming to do this, to take this approach to graphing a polynomial. So we're going to do something faster and I hope better. One important way to do a faster job of graphing this function is to really focus more on the factored form of this polynomial. And first I want to think about questions like, when do I get 0? In other words, what can I plug in that will give me a value of y equal to 0? So for instance, let's ask, is f of 5 equal to 0? Rather than finding an exact value for f of 5, let's just sort of write out formally what we get. So 5 plus 1 times 5 minus 3. And the question is this equal to 0? The answer is almost immediate. I know it's not equal to 0. And the reason I know it's not equal to 0 is 5 plus 1 is 6. So in particular, that's not 0. And 5 minus 3 is 2. So it's also true that that's not 0. Oops, not 0. So what do we have? We have a product of two things, and both of those numbers are non-zero, so therefore the product is absolutely not 0. So f of 5 is not 0. What's f of negative 2? The same sort of thing is happening. It's going to be negative 2 plus 1 times negative 2 minus 3. And regardless of what the exact value of that is, I know that negative 2 plus 1 is definitely not 0, and I know that negative 2 minus 3 is definitely not 0, so this whole product is not 0. And you might say, well, that doesn't help much because it's not all that useful to just know that something is not 0. And maybe that's true, but that might give us some insight about how to know whether something is 0. So now let's think about f of 3. So again, looking at the factored form, that's 3 plus 1, which happens to be 4. But then we multiply it by 3 minus 3. And at this point, it becomes irrelevant that 3 plus 1 is 4. All we really have is some number, happens to be 4, and we're multiplying it by 0. And the reason we know that's 0 is because 3 minus 3 is 0. And it doesn't matter what we multiply by 0, we're going to get 0. So f of 3 is 0. And in fact, there's one other number we can easily see that we can plug in, and it gives us 0. F of minus 1, that's going to be minus 1 plus 1 times minus 1 minus 3. And that's 0 times negative 4. And sure enough, that's equal to 0. So the point is, our function is built out of two pieces that are being multiplied. And if you can make either of those pieces 0, their product will be 0. So f of 3 is 0, and f of minus 1 is 0. And that explains exactly why we have this point, 3, 0, and we have this point, minus 1, 0 on the graph. The summary of all of this is that the factored form of a polynomial tells you pretty quickly what the x-intercepts of a polynomial function are. As soon as you see how to make one of those pieces equal to 0, then it becomes immediately clear how to make the output of the function equal to 0. For instance, if you plug in x equals minus 1, then the output of the function is 0. But it turns out that the factored form of a polynomial tells you a little more than just how to make the output 0. It also tells you whether or not the output is bigger than 0 or less than 0. And it's not so hard to figure that out. So to help see this, I want to look at f of 1. Then I want to look at f of 1.5. And then I want to look at f of 2. And I want to see, even if we did f of 2.5, I want to see that there's a certain amount of commonality in all of those examples. So let's start by looking at f of 1. And again, we're not going to pay attention to the standard form. We're going to look at the factored form. So what's f of 1? Well, if we're being really diligent, we would say, oh, it's 1 plus 1, which is 2, times 1 minus 3. And that's 2 times negative 2, and that's equal to negative 4. But really, instead of thinking so much about the details, I just want to think about the fact that 1 plus 1 is positive, and 1 minus 3 is negative. And when you multiply a positive times a negative, you get a negative. So f of 1 is negative. And maybe rather than writing the negative sign, I'll just write neg. So f of 1 is negative. Now let's do f of 1.5. Okay, well, what's that? It's 1.5 plus 1 times 1.5 minus 3. And again, if we pay attention to some of the details, but not all of the details, 1.5 plus 1 is positive, 1.5 minus 3 is negative, and so this whole product is going to, again, be negative. And look, we got the same thing that we got before. We had a plus sign and then a minus sign. So the first factor was positive and the second factor was negative. Now we're going to do f of 2. We could do f of 2.5. It would be exactly the same. So what's f of 2? It's 2 plus 1 times 2 minus 3. And what's this equal to? Well, again, 2 plus 1, it happens to be 3, but all I really care about is that it's positive. 2 minus 3, all I really care about is that it's negative. And so this whole thing is going to be negative. And what this is really saying is that the graph of this function lives below the x-axis when I plug in 1, when I plug in 2, when I plug in 2.5. In fact, let's think about, what if I did even f of 2.9? F of 2.9 is 2.9 plus 1. Well, that's still going to be positive. Times 2.9 minus 3. And even though it's 2.9 minus 3, 2.9 is pretty close to 3, but it's still less than 3. So in fact, 2.9 minus 3 is still negative. And so this product is still going to be negative. And really, this is kind of illustrating the big point here, which is that nothing's going to change if I keep plugging in numbers between -1 and 3. So if I had plugged in 0, I still would have gotten a positive number there and a negative number there. If I had plugged in 2.8, I still would have gotten a positive number there and a negative number there. And really, the only way, for instance, that I could change that second factor to give me a positive number is if I plugged in something bigger than 3. If I plugged in something bigger than 3, then suddenly 4 minus 3, 3.1 minus 3, 3.2 minus 3, they're all positive. So the point is, this factorization tells us that no matter what numbers we plug in between -1 and 3, this graph is going to be below the x-axis. You could do a similar analysis by plugging in numbers that are bigger than 3, and no matter what you plug in bigger than 3, that graph is going to be above the x-axis. Let's actually try plugging in something less than -1. So if I plug in something like f of -1.2, what do I get? I get -1.2 plus 1 times -1.2 minus 3. And the point is that -1.2 plus 1, that's negative. And then -1.2 minus 3, that's also negative. And it wouldn't have been any different if I had used -1.5 or -8 or -17. And so I would get a negative times a negative, which is a positive. And that's why the graph is above the x-axis. In this example, we have pretty modest goals. We're going to figure out two things. First of all, where does the graph hit the x-axis? Those are called the x-intercepts. And then where is the graph above or below the x-axis? We're going to leave the details of drawing the actual graph for a later time. So right now we have just pretty modest goals. So let's think about where this graph hits the x-axis. Again, I haven't even given you the standard form of this polynomial. I've just given you the factored form. And I hope based on that last example, it's pretty clear that if we plug in 2.5, we get, well, 2 times 2.5 plus 3, that happens to be 8, but let's just say it's something positive. And then 2.5 minus 1, that's 1.5, but let's just say it's something positive. And then 2.5 minus 2.5, that's 0. And so that gives us 0 when we multiply those things together. So the key is that there is a dot on the graph right there. There is an x-intercept at x equals 2.5. Similarly, if you plug in 1, what's f of 1? Well, it's 2 times 1 plus 3. And again, that happens to be 5. I don't even really care that it's positive. It's just some number. Then we have 1 minus 1. That's 0. And then we have 1 minus 2.5. And again, let's not worry about the details. It's some negative number. And so the whole point is that this product of three numbers is going to be 0. So f of 1 is 0. So there's another x-intercept right there. The last x-intercept is somehow coming from this factor. It's a little bit harder to find it. And one way that you can see what that x-intercept is you can set that factor equal to 0. You can say, what would it take for 2x plus 3 to be 0? The answer is x would need to be equal to minus 3 divided by 2. So minus 1.5. And now if we plug in minus 3 halves, f of minus 1.5, what do we get? Well, that first factor, I mean, if we want to, we kind of know what's going to happen, but if we want to, we can actually go through the details. 2 times minus 3 halves is minus 3. Then we add 3. That gives us 0. And then we have some negative number and some other negative number. And so this becomes 0. So the point is, we have yet another x-intercept right there. So the question is, does the graph look like this? Does the graph look like that? Or does the graph look like that? Or is it something entirely different? There are lots of things that I can imagine going through those 3 points. And the way we're going to figure this out is we're going to test whether certain outputs are positive or negative. At the bottom of the page, you should see what is basically an enlarged version of the x-axis. And I've labeled the most important numbers, the numbers that are x-intercepts. So now what I'm going to do is I'm going to test a number that's, say, between 1 and 2.5. I'm going to plug it into our function and see what I get. So a good number to test would be something like 2. So what's f of 2? It's equal to 2 times 2 plus 3. That's a positive number. 2 minus 1, that's also a positive number. And then 2 minus 2.5, that's a negative number. So what do we get here is we get a positive, and a negative. And when we multiply those together, we get a negative. So that means that the graph of f of x is somewhere down below the x-axis on that region. Now let's pick a number that's bigger than 2.5. The point is that it doesn't really matter what number we pick that's bigger than 2.5. So let's do f of 3. If you're adventurous, you could do f of 4, or if you're adventurous, really adventurous, you could do f of 40 million. All these things are going to give you the same answer. So what's f of 3? 2 times 3 plus 3, that's positive. 3 minus 1, that's also positive. 3 minus 2.5, that's also positive. That means that the graph of f of x is above the x-axis when x is bigger than 2.5. So here's 2.5 up here. The graph is above the x-axis there, and it's below the x-axis on the other side. Now, let's pick a number between minus 3 halves and 1. Probably the easiest thing to pick is 0. But any number you pick is going to give you the exact same sign in the end. So what's f of 0? It's 3. times 0 minus 1, that's negative 1. And then 0 minus 2.5, that's negative. So f of 0 is a product of three numbers, two of which are negative. So f of 0 is actually positive. And then finally, I need to pick some number that's to the left of minus 3/2. So let's do something like f of minus 5. That's going to be negative, okay, if I plug in negative 5, that's going to be negative 10 plus 3. It's too hard to do, but I do know that it's negative. And then negative 5 minus 1, that's also negative. And finally, negative 5 minus 2.5, also negative. So the product of three negatives is negative. So what does the graph of this function look like? We've got these three x-intercepts at negative 3/2, at 1, and at 2.5. And it looks like the graph is above the x-axis, then below the x-axis, then above the x-axis, and then finally below the x-axis. And this picture that I've drawn is a pretty terrible picture, but it gets across the basic idea. In reality, there won't be any gaps in the graph. It will be very smooth, no sharp corners, and we'll see on the next page exactly what it looks like. So this is the actual picture of the graph of that function. It's worth pointing out that we got things basically right. We made some mistakes, right? The graph turns out to be a little bit taller between negative 3/2 and 1 than I thought it was. And it doesn't go very far down between 1 and 2.5. But again, the basic idea is right. It's also worth pointing out that this point up here, that's called the y-intercept, that would be pretty easy to find. It's f of 0. And if you figure out what f of 0 is, that ends up being 3 times negative 1 times negative 2.5. So that's 7.5. That would have been a little bit easier to figure out if it had been written in standard form, but it's still not too hard. This next example looks easier in some ways and maybe harder in at least one way. So one way that this looks harder is there's this minus 0.4 in front, and we'll have to think hard about what that actually does. It looks easier in the sense that there seem to be fewer factors, although we should remember that x minus 1 appears twice. It has a multiplicity of 2 that really stands for x minus 1 times x minus 1. We'll see what the impact of that is in a little bit. I hope at this point you're feeling fairly intuitive about the idea that this factorization tells us about the x-intercepts. So you might be unsurprised to know that f of 1 is equal to, technically it's minus 0.4 times something times 0 squared, but that's equal to 0. So there's an x-intercept at x equals 1, and there's another x-intercept. That one might not be quite as obvious. It's the one that comes from this factor. And the idea is if we could make 2x plus 5 equal to 0, we would have another x-intercept. And so minus 5/2 is the other x-intercept. So if you do f of negative 2.5, you're going to get minus 0.4 times 0 times something. And that's going to be 0. So we have another x-intercept that's here at negative 2.5. The question now is, what does the graph of this function look like? Does it look like this? Does it instead look like that? Or does it look like something different? And we'll see that the answer is it actually looks like something different. So to figure this out, let's do the same sort of thing we did before. We know that there's an x-intercept here and an x-intercept right here at minus 2.5. Let's make an enlarged version of that x-axis. Here it is. We'll mark off x equals minus 2.5 as well as x equals 1. And we'll plug in some numbers between those numbers and on the far right and on the far left. So for instance, a good number that's between negative 2.5 and 1 is 0. So what's f of 0? And we have to be a little bit careful. Here's where that minus 0.4 actually matters. That minus 0.4 is just some negative number. If you didn't see it there, I wouldn't even be writing anything here. And then 2 times 0 plus 5, that's positive. And of course, we have a negative number, 0 minus 1, but it is squared, and that matters a lot. Because what we actually have here is a product of 4 numbers, negative, negative, positive, negative, and altogether that gives us a negative. So that means that between negative 5/2 and 1, our function is below the x-axis. In fact, I'm even going to write the word below here. Let's plug in a number that's less than minus 5/2. So a good example would be something like f of negative 10. What's f of negative 10? Again, you have this negative 0.4, and then you have 2 times negative 10 plus 5. That's going to be negative, whatever exactly it is. And then you have negative 10 minus 1, and you're squaring that. So what is this? It's a negative times a negative times a positive, so that's going to be positive. And that means that f of x is positive when x is less than negative 5/2, and that means that the graph of f of x is above the x-axis. At this point, here's where the plot twist happens. You might expect that there's going to be this alternating pattern where the graph goes above, below, above. But it's not going to happen, and it's really coming from the fact that this factor has a multiplicity of 2. So let's see why this is. I'll even use a different color for this. So let's pick a number bigger than 1. 2 is as good as anything. What's f of 2? Well, it's equal to negative 0.4 times, now we have 2 times 2 plus 5, that's positive. And then, of course, we have 2 minus 1, that's positive, and we're squaring it. And actually, if you just kind of figure out what this product is, it's pretty clearly going to be negative. And that means that f of x is negative when x is bigger than 1, and our graph is below the x-axis. Now, why didn't it make a difference? Why did the graph not change from below to above? It really comes down to the fact that this factor up here had a multiplicity of 2, and 2 happens to be an even number. And the key is that when you square a negative number, it becomes positive. If you square a positive number, it stays positive. So that explains why there's really no difference between f of 0 and f of 2 in some sense. And it boils down to the fact that squaring a negative, squaring a positive doesn't really change what you have. So what does this graph actually look like? I mean, again, we're not trying to get a pretty picture right here. We're just trying to do something really rough. But the idea is that this graph is going to be below the x-axis here, and it doesn't cross the axis, it stays below, and then eventually it gets above the x-axis over there. In reality, the picture is going to be a little bit more extreme than what I've drawn, but that's the basic idea. Here's a nice version of that picture. And as advertised, the graph is below the x-axis over here. It's below the x-axis between negative 5/2 and 1. And then, of course, it's above the x-axis when we get to the left of negative 5/2. Here's our last example. In a lot of ways, this is very similar to the previous example. There's kind of one new twist that you may not even really realize until the very end. But let's start as we did before. Let's think about what might the x-intercepts be. I hope it's pretty clear by now that if you plug in 3, you get some number, happens to be negative 0.4, times some other number, and then you get a 3 minus 3, which is 0, and you happen to be squaring that, so that product is going to be 0. And then similarly, if you plug in 1.5, now you may ask, where's 1.5 coming from? Technically, it's coming from 3/2, and that's because I was looking at how to make that thing 0. And the answer is, how is 2x minus 3 equal to 0? You set x equal to 3/2. So f of 3/2 is going to be negative 0.4, just some negative number. And then when you plug in 3/2, that middle factor is going to be 0. It's cubed. And then, of course, 3/2 minus 3 is just some negative number, and you square it, and what do you get? You get 0. So that tells us that there are 2 and only 2 x-intercepts. One of them's at 3, one of them's at 3/2. So we have an x-intercept here and an x-intercept right there. As usual, the question is, what does the graph of this function look like? Does it look like this? Well, it can't look like that. That's a silly picture because we know we only have 2 x-intercepts, and I just added a third one. So maybe it looks like this. Maybe it looks like that. Or maybe it looks like that. Or maybe it looks like something else. And we'll see it's something else. So let's test where our function is above the x-axis and where our function is below the x-axis. Let's do something like f of 4. And again, f of 4 should be no different than f of 5 in terms of whether it's positive or negative. F of 6, f of 3.1, anything over here. So f of 4 is going to be negative 0.4 times, we got to do 2 times 4 minus 3. That's going to be positive. And then we have 4 minus 3. That's positive. And I forgot that we're actually cubing that middle factor and we're squaring the last factor. So altogether, it looks like we have a negative number here. So that means our graph is below the x-axis here. Now let's do something between 3/2 and 3. There aren't a lot of simple numbers here, but let's use 2. I think that's a good one. So what's f of 2? Well, it's going to be negative 0.4. Actually, I'll do it down by the graph. It's going to be negative 0.4. And then we have 2 times 2 minus 3. And that's going to be positive. And then finally we have, oh, but I'm cubing that. And then we have 2 minus 3. And that's negative 1. In this case, negative is all that I care about. But I'm squaring that. And since I'm squaring that last negative number, I still get negative times positive times positive. And negative times positive times positive gives me negative. That means that our graph is still below the x-axis. And maybe we're not surprised by that at this point because this x minus 3 has an even multiplicity. So again, we got negative and negative. Now let's plug in something that's smaller than 3/2. And I suppose the easiest thing to do is 0. So what's f of 0 equal to? Well, it's negative 0.4 times 0 minus 3, that's negative, and we're cubing it. And then we have 0 minus 3 squared. So what does that all work out to be? We actually have a negative times a negative when we cube that thing times a positive. So negative times negative times positive, that's going to work out to be positive. And so our graph is therefore above the x-axis here. So with all this in mind, you might expect that the graph's going to look something like this. And that's a pretty good guess. In fact, that's actually not too far from what the graph really looks like. And we'll see in just a moment that the real graph, in addition to maybe being a little bit more extreme, maybe it gets farther down or grows or shrinks more quickly, something kind of different happens right around that part of the graph. So let's see what that looks like. Here's the actual picture of that graph. And the thing that happens that's a little bit interesting is this graph kind of flattens out as you get close to 3/2. And then after it gets past 3/2, it starts going down again. So I want to think about why is that? But again, this is a pretty fine point and you shouldn't worry about this too much. The gist of it is that the graph is below, below, and then above. So it's pretty likely that in some math class, you've graphed each of these 3 functions that's written at the bottom: y equals x, y equals x squared, and y equals x cubed. And let's just quickly recap what those things look like. So what does y equals x look like? Well, that's a line at a 45-degree angle through the origin. So that one I hope is just a pretty familiar example. Now let's think about what does y equals x squared look like? That's not a line. It's your old friend, this parabola, and it looks like that. By the way, that reminds me a little bit of how that function looks at this x-intercept that has a multiplicity of 2. Now let's think about what happens when we graph y equals x cubed. I'm going to do that in red, and I'm going to leave y equals x squared up there. So when we graph y equals x cubed, it looks something like this. And actually, I should be a little bit careful about where the green graph and the red graph are above or below each other. But right now, the point I really want to get at is just that this red graph, this graph of x cubed, kind of flattens out when you get close to the origin. And that's similar to the behavior that you see near this x-intercept of 1.5. And again, the kind of analogous or important thing that's happening here is that that factor, that corresponding factor of our polynomial, has a multiplicity of 3, much like this third power that we see above x.